It's a pleasure to have Audrey here for the last talk. We should talk about streaming kernel regression.
Hello, everyone. I hope you are not too tired. I'm just glad to see that there are still some people in the room. So thank you for staying to my talk. So this is a joint work that I've done with Audrey at INRIA, Lille, and Joël, who's currently the supervisor of me as a postdoc in her lab. And so, yeah, the idea behind this work is that I am from more practical side, though I am drifting slowly toward theory. And Audrey is more of a theoretical guy, and we were talking about how sometimes the assumptions that are made in order to solve problems do not really apply in practice, and what are those assumptions that we could try to relax to make the work more applicable. So that's the idea. Here, especially, we'll be talking about how we can perform streaming kernel regression and maintain confidence intervals while not knowing the variance of the noise, which is something that is often assumed to be known when you do streaming kernel regression to get results. So let's start with a simple example. Imagine that you want to optimize the treatment dosage for a given disease. So you have patients that come in one after the other, and you try to cure these guys the best as you can, but at the same time, you're trying to search for the optimal treatment. So you must, on one angle, try to make some exploration. So try new dosages that are not, given the observations that you have, may not appear to be the optimal, but maybe they hide some information that could allow you to improve your solution. Or you can just try to focus on giving the best treatment that you know right now, such that you cure the people the best as you can. And more specifically, in this kind of problem, there's something that you can exploit to get, to learn faster. It's the underlying structure of action. So every time you try a dosage on a person, this gives you information about the effect on that dosage, but also information on the dosage that are close by. So we'll see how we can work out with kernel regression in that kind of problem. So that was just a nice example, but if we take the more general case, that kind of problem comes back to an online optimization problem of a function that you don't know. So on every sort of episode, if I can call it this way, you need to pick a point that could be a dosage, and then you observe. Then you get a noisy observation of the function at that point. So that would be observing the effect of the treatment on a patient. And then you repeat, and you roll like this. While you try, well, the goal as you roll like this is to optimize. So let's say you want to maximize, in the case of maximizing the treatment effect, for example, or to minimize, if you were trying to minimize the side effects of treatments, this unknown function. So you're trying to learn the function as you're trying to behave properly by using that function. So as you proceed in such a problem, you face the situation where, as you gather observations, you maintain a model with your observations, and that model helps you pick the next point. So you are in this sort of cycle problem where your model depends on your observations, and your observations depend on your model. So you cannot analyze these kind of settings the same way you would to provide, for example, kernel regression bounds on IID samples. Your samples are not IID, your samples are based on your model. In this talk, the model we'll be talking about will be obviously a kernel regression model. So I'll start by giving you some kernel regression background, just to refresh the memories for those who haven't heard about these things for a long time. Give some results, and then I will introduce some strategy to adapt the regularization of the kernel regression based on the empirical noise on the observations that you have gathered up to now. And then we'll show how this can be applied to kernelized bandits. And if we have time at the end, I will show you also a real-world application where this has been deployed. So let's start with some results and background in kernel regression. So we'll start with the easy case of the linear regression that all of you must know. So imagine you have this blue function that has generated noisy observations shown as blue dots. So we store these. We store the data points in the matrix X and the observations in vector Y. And given that it's a linear function, so your function can be represented as a product between your point and a parameter theta. Then, using ordinary least squares, you can easily compute an estimate, theta n, based on the n previous observations. And then you can obtain a predictor of the function at any point by doing the product between any point with the estimate that you've computed. So it's easy when your function is linear. When your function is nonlinear, but you have a kernel function phi that can send your projected points, your points in X into a projected space K, where your function can be expressed as a linear combination between the projected points and a parameter theta, then you can solve it exactly the same way as you did before. By computing an estimate that uses, instead of using the data points in X, they use the projected points, and you compute the ordinary least square like that. And you could have a predictor for your function at any points. The thing is, the product of the matrix of the projected point, so phi n, when you do the product with itself and you try to invert it, it might not be invertible. So in practice, we deal with that by adding some regularization on the diagonal. So some little lambda to make sure that the system behaves well and that it can be computed. Okay, so we have this form. Everything looks nice. Okay, we regularize. That's nice. But the problem is the projected points. They are in space K, and this space K may be of very large dimension, which we call here d prime, and this d prime can be up to infinite. So it's possible that your kernel function, your phi of x, is of infinite dimension, and it's possible that your matrix and your product matrices are of infinite dimension in one direction or another. So that's a problem in practice. It means you cannot explicit them in your computer and actually compute these quantities like this. Fortunately, there's an alternate form in which you can rewrite the estimate. So now, what you see is that you don't have phi n transpose phi n, but you have phi n times phi n transpose. And this guy now has dimension n by n instead of that d prime by d prime, which is cool. Okay, so this one, we can just push it away. We know we can now express it in a finite form. But we still have the first one at the left that still has dimension d prime by n. So still an infinite dimension in one direction. What we do here to deal with that is that we use what they call the kernel trick. So we define the kernel as being the product of two projected points. And by introducing the kernel matrix, that is a matrix that computes the kernel between every pair of points, and the kernel vector defined for some point x that computes the kernel between this point x and all the previous observations n, then you can rewrite the predictor as this. So as you can see in this equation, there are no more infinite dimension quantities. You can compute this. Its closed form is easy. So it solves everything up to now. So here are some examples of these, the kind of predictors that you would obtain for different values of regularization. So you see that the regularization plays a huge role in the kind of models that you can handle. If you regularize a lot, you are forcing your function to stay close to zero. You're not allowing much. You're not allowing your function to move a lot in the space. If you decrease the regularization, you can handle functions that are more funky, but that might overfit your exploration. So there's a trade-off, and the question of what is the good regularization is in itself a good question. Now, if you put some assumptions on the observations, so let's say here, for example, that the noise that is added to the observation is Gaussian, and that your parameter theta is sampled from a multivariate normal with covariance sigma. And more specifically, we consider the case where sigma is defined as the noise over some lambda. Then in this setting, with these priors, for those that are familiar with Gaussian processes, you find out that you can actually compute a posterior distribution on your function, the function that you're trying to retrieve, that is parameterized by, as the mean, the predictor, and as the covariance, a function of the kernel, and this noise over lambda. Now, in practice, if you want to sample from such a distribution, because that distribution is good for giving you confidence and envelopes and lots of information like this, but it's also, it's a distribution, so you can't really sample a function from it. But if you want to sample a function from it, you will need to evaluate this at a discrete finite set of points. So even though the formulation that we had on the previous slide is true, like, in theory, in practice, you can really just have access to a sample function that is discretized. And for example, here are some samples that you can draw from such a distribution. So you have your predictor, that is the mean orange line. You have, I think this is one standard deviation, one predictive standard deviation at every point, and you have, as green dotted lines, some functions that were drawn of it. So it's nice. It's a generalization of the normal distribution from which you can sample variables to a distribution from which you can sample functions. You can say it like that. Now, what kind of results do we have with these models? So let's just remind us of the initial problem. So it's a sequential problem. You pick your point xt, you get observation yt. The choice of xt is based on the model conditioned on the previous observations. So it's not IID, it's self-influenced. Well, in the literature, you can find confidence envelopes like this that tell you essentially that the error that you are going to make when you use your predictor to predict at some point is bounded by some quantity with some high probability. Well, one thing that is really great about this is that it's true simultaneously over all your space. So it's not just controlling the error that you're making at one place. It's controlling the error that you're making over the evaluation of your function over all the space, but also simultaneously for all observations. So it's not just saying that the error that you're going to make at one step is bounded. It's saying that if you're doing one run over, like, let's say, large T episodes, well, if things go well, they go well over the complete run, not just over a single episode. Now, if we look at the little quantities that appear in there, well, first, obviously, you find some inverse dependence on your confidence. Well, for those who are not familiar with these kind of things, you can think of the confidence and the confidence envelope being related in the way that the confidence envelope is just some space that you define, where you say, I know that I have the confidence that the true model lies in this space. Of course, if you want to say such thing with a higher confidence, the only thing that you need to do is to increase the space in which you make your claim. So that's why the more confidence you want, the larger the confidence envelope you'll be considering. Then you also see that there is this term here that appeared in the posterior covariance. So this term here, you could relate it if we were talking about normal, the posterior of a normal distribution. This would be related to the posterior variance, so the posterior confidence that you have over where your model is. So it makes sense that it is there. Then you see this guy. So the norm of the function in space K, you can see it as representing the complexity of the function. So a function that has very high peaks, very sharp slopes will have a larger norm. So of course, if you have a function that can vary very quickly, then in this case, whatever the observations that you gathered, like you have less confidence. If you have some spot that you haven't yet explored, you don't know what the function could be in there. It could change a lot, and maybe you would be making a lot of error in that space. That's why you find this guy here. And finally, the last but not the least term is what we call the information gain. So this term tells you how much information you can get using another additional observation, wherever it is. So it's the maximal information that a new observation can bring. So let's look a little bit into this quantity because it might not be obvious and it's interesting. So here you have two examples. So in a case of linear regression, so linear kernel regression and Gaussian kernel regression, you have different models that were conditioned, so that the plain lines is the model conditioned on the blue observations only, without the pink one, and the dotted lines correspond to the model that was the same color in the plain line, but now we have added the pink observation to it. So what you see is that you have some kernels, like the linear kernel, that share very well the information across the space. So even when you add another observation, the model does not change much. What you gain as information is not that much. While you have other kernels, like the Gaussian kernel, that only look at the observation in their neighborhood. So when you get a new observation, if it is in a place where you did not have much information, it can cause a huge change into your model, especially if you have a small regularization, because in this case, you allow your model to follow well your observations. So this shows a bit how information gain goes. Concretely, these are the curves of the information gain as you get more and more observations for the same models that were depicted up there. So what you see, note that the scales on the y-axis are not the same. The linear regression models, they accumulate they accumulate less information gained as they go than the Gaussian kernel regression models, obviously. And the lower the regularization, the more, the larger the information gain grows. So recall that the confidence envelope is proportional to the information gain. So you can imagine that the confidence that you have, if you have a kernel that does not share a lot of information and that you allow to overfit your observation a lot, will have less confidence than a model that is very well regularized and that shares information very quickly over all space. Oh, these are nice figures. Formally, they correspond to these quantities. So this is the formula of the information gain, which is just by applying the kernel. And the order of these curves are shown here. So yeah, you clearly see that the kernel regression model has a higher order of information gain. Okay, so this is the results that we were talking about earlier. Recall that we had this prior. Now, an interesting case for regularization is this quantity here. And why would we pick this quantity? Well, it sort of makes sense when you look at the prior over sigma. Like, you would like to have a lambda that depends on, obviously, the noise, that depends also on sigma, but putting some prior over sigma does not make really sense in practice because we have no idea what this matrix would be, and this is an infinite by infinite matrix anyway, so how could you ask someone to put anything and to define any such matrix? But if we consider if we consider lambda as being the noise over the squared norm of your parameter theta, which is equivalent to sigma over the squared noise of the function in space k, well, what we observe is that the posterior covariance and the confidence envelope can rewrite as very nice quantities. So just the fact that these equations simplify nicely, well, it gave us the intuition that we were not too much on the wrong path. We don't have the guarantee, but everything seemed fine. And the kind of confidence envelope that we would obtain by setting the regularization as this quantity would look like something that you have up here. So you see that, well, your model is inside the confidence envelope, so it shouldn't be too bad. Like if you're claiming that the model, the true function is in the orange zone, where, well, you're fine. It is. Okay, cool. So we have a way to set the regularization, but the problem is in practice, the variance of the noise, so the sigma, and the norm of the function, they are not known. So we cannot, like, realistically ask someone to put these quantities. So what are we going to do? Well, usually what people do is that they assume that they know an upper bound on the noise and that they know an upper bound on the function. Well, not on the function, but on its norm. And they end up with a confidence envelope that look like this, compared with the confidence envelope if you would have known the true quantities. So it's a bit disappointing, right? You look at this and, well, it seems like we don't know anything anymore. I could almost have said, well, the function is anywhere, and would have looked the same. But when we look at what happens when the upper bound on the noise gets closer to the true noise, we see that the confidence envelope is not perfect, but it is not as ridiculously huge as it was before. So maybe there is something here. Maybe if we could adapt this upper bound on the noise in some way that it gets closer and closer to the true noise, we would be able to get something that gets closer to this without actually knowing the noise. So this is what we're going to do. Yes?
I'm a little confused about why there's so for the norm of the function, which is in the denominator for the lambda, would you usually not have a lower bound so that you always overestimate the lambda? Because if you have like a very high C, your lambda is extremely small. I might just be missing the function.
Well, if you regularize, well, okay. If we come here, what you see is that the norm of the function, is the confidence envelope is linearly dependent on the norm of the function. So if you use a lower bound there, you'll be considering a confidence envelope that is too tight. That's why we do it the other way. Okay, so how do we do that? How do we get this bound on the noise? Well, we start with the following empirical estimate of the noise variance. That you know, you just compute the squared deviations between the observations that you had, all the past observations, and the predictor that you've computed on these past observations, and that's easy. Unfortunately, when you look into the literature, you find that Audrey has been doing many things, like providing these confidence intervals that you can have on the empirical noise estimate. So what you have here is an upper bound on the noise, on the empirical noise, and a lower bound that both tighten at speed 1 over root t, which is nice. And again, similarly as what we had with the confidence envelope on the kernel streaming regression, it's still valid for all observations that you have. So these are also bounds that are true for the whole series of observations that you'll get along the run, and not for just one time step of observations. Okay, so we have this. This is nice. We want to use this guy. Obviously, why not? It's so easy, right? We cannot avoid it. This is what we want. We want to use an upper bound on the noise. Okay, so let's say we want to define the regularization as this upper bound on the noise squared over the upper bound squared of the norm of the function. Okay, but it says that you need to have, in order to compute this upper bound, you need to have a lower bound. We call it lambda star on the lambda that is used to compute the upper bound on the noise. How do we get this lambda? Well, it's easy, right? If you have a fixed lambda, you can just, the upper bound is the same lambda. It works itself. And you get the following upper bounds on the noise. So you have two examples here for two different starting upper bound on the noise. So you see they get her observation, and at some point when they have enough observations, then the system starts to learn the noise and they get lower. But, well, I am not too happy with these curves. What if, instead, we were able to adapt the regularization that we use in this upper bound by using the regularization that we want to adapt for our kernel regression model? Then we would get these curves, which I think are much better. So, I did not mention, but the true noise that we are estimating with these is set to 0.1. So bottom line is the target. We would eventually reach it far, far, far away. Asymptotically, not really, we won't touch it, but we'll get close to it at some point. Yeah, so, okay, we want to use this. But if we want to use this, then we're stuck with the need of a lower bound. Like if we are replacing our lambda in our estimate with something that is not a fixed lambda, then we cannot consider that lambda star is equal to lambda anymore. We need to come up with some quantity that will lower bound our lambda. So intuitively, if we are tuning the lambda by using upper bounds on the noise, then we know that the lower bound that we're ever going to reach is the lambda that would be defined by using the true noise. Okay, cool, but we still don't know the noise of the variance. That's the whole point of doing this. So if we knew it, we would not be doing all this. Fortunately, the result up there provides two bounds, an upper bound and a lower bound. So the thing is, we're going to use that lower bound to compute a lower bound on lambda star, which we'll call lambda minus. And we're going to use that lambda minus in order to compute our upper bound on the noise. So it will be a two-step estimation. So yeah, I'm just saying that all these things will remain. If we proceed as such, we'll just end up with an upper bound on the noise that is a bit looser than the one that we would have if we really had access to a true lower bound and a true upper bound. So here's a summary of the resulting procedure. So you start with an upper bound and a lower bound on the noise that may be loose. And then on each time, you compute the lambda based on the upper bound on the noise that was computed previously. Then you acquire your noisy observation, and then you compute a lower bound. And then you compute your lambda minus based on that lower bound, and then this allows you to compute your upper bound finally. And you put this back in, and you turn it like this, and it provides the following confidence envelopes on the estimation of the noise. So you can see that as you go on, the way you estimate your noise is tighter and tighter. So it's for estimating a noise of 0.1. So so given that if you start with an upper bound on the noise that is already set to the good noise, what you see is that it's just that it will stay constant, and your lower bound will get closer and closer and closer to it, and that will be just it. So it seems like we have something now from which you can estimate like an upper bound on the noise and the regularization. So if we go back to the result that we had for the confidence envelope using the fixed regularization, what we want to do is to extend it to now a predictable sequence of regularizations that we determined given the previous observations that requires the same lower bound here for two different reasons. One reason being for the estimation of the noise, the other reason being for the proof of with a fixed regularization to be able to extend to this case. So I'm not going to show the proof here, but it's very minor detail. If you have this quantity, everything holds, it's fine, and already needed the quantity for the upper bound on the noise anyway. Yes?
What does it mean when the larger than lambda star? What are the implications of that?
That we have a lower bound lambda star? You mean why did we need that for the theory, or what does it mean in practice?
It means that you have like a lower bound on the smoothness or something?
No, it means that you are it means that your regularization will never get lower than the regularization that you would have defined if you had known the noise.
So normally you have some kind of lower bound on the smoothness of your regularization.
Yeah, so you have the target of regularization that we want to have, and you're just asking that the way you adjust your regularization is such that you arrive from above and you get closer and closer to it, but you never like go down and up and down and up like this. That's the only requirement. But if you have any way of tuning it that arrives from the top, it's fine. The proof will apply also. So here we have our own way of tuning it, but any other way that would respect that would be fine. So what we were able to compute is the following confidence envelope, where you can see the adapted regularization. So we still have this quantity here that we could replace by C, and this that we could replace by an upper bound, but everything is in there. You see that the lower bound appears in the information gain because, as I explained before, the information gain grows larger when you have a smaller regularization. So you must consider the smallest regularization that you can achieve using your tuning, which is given by that lower bound here. So this is why you have this guy here defined over lambda star. Oh, well. And you see the simplification here. So if we replace lambda t plus 1 by its definition, well, it simplifies given the choice of regularization that we had picked in the beginning. And we obtained the following corollary that extends the result for fixed regularization to the setting where we adjust. Okay, so let's see how interesting is that result in practice. So here you can see the confidence envelope during the regularization adaptation process compared with the confidence envelope if you already knew both the noise and the true norm of the function. So we are really comparing against like an oracle here. So you see that as we get more and more observations, we get closer and closer. So this seems nice. There's still a little gap. Like it's hard to gauge from here like how bad or good this is. So let us compare it with what we would have had if we had stick to the upper bound on the noise and the upper bound on the function norm. What we see is that what we are getting, well, it might not be perfect, but it is clearly really better than what we would have had if we had just stick to the fixed lambda. So we were happy with that. And now, since we had all our things that seemed to work out, we went to see how can we apply this to something. And of course, kernelized bandits seemed like a proper application for the tool. So for just a quick refresh, though we have been talking a lot about bandits during the workshop, so you must all know lots of these things. In this setting, we are trying to optimize a function. So on each episode, you pick a point, you obtain a noisy observation, you want to maximize f. So let's start define the point that maximizes f. Our goal will be to minimize the cumulative pseudo-regret as expressed as this quantity here that is very similar to the usual regrets that you see in all these different bandit settings. So the only requirement that we have here is that the function f actually belongs to the space k defined by our kernel, meaning that its norm in the kernel space must be bounded, must not be infinite. If it's infinite, your confidence envelope is infinite also. So you cannot say anything. So first we looked at how we could apply this in UCB. So UCB was a good candidate for that, very easy. So you just compute the the optimistic value of the function by taking the predictor and you add to it the confidence envelope, and you just pick the max point in there. When you do that, what you get is a bound like this. So that a bound that depends on the norm of the function, square root of t, and the information gain. So if you compare with what exists, you can find some results. So different approach for kernel UCB that is able to obtain a tighter bound, but they assume that they have bounded noise and bounded function, and that these bounds are known. So it's a bit more restrictive. They also depend on some d tilde d quantity, which is something that is a bit tighter than the information gain, but they are related. So we could say that the information gain is some sort of upper bound on this quantity, which is like the effective dimension of your input space. So what dimensions actually play a role in your in making your function change a lot. So if we compare to if we look at the linear case, so our bound, if we take the upper bound on the information gain given the linear kernel, the kind of bound we get is this. And if we compare, for example, with the lower bound that exists in the setting for continuous and finite input space, then we see that we don't seem to be that bad, given that we're not giving our algorithm lots of information, right? We're not bounding anything really. We allow it we allow the model to behave without too many restrictions, and we don't even know the noise when we tune. So we were pretty happy with that. I'm not aware of any lower bound for the kernel setting though. So maybe some of you know about it. I'd be interested in knowing if you have something in mind. Okay, so now empirical experiment. I told you that I am the experimental person in this collaboration, or I was, at least in the beginning. So I've been playing with these things a little bit. So consider this example here. So it's just a simple function that was generated from a Gaussian kernel. So with the given parameters here and a given noise. So we compare three versions of kernel UCB. One that uses the complete knowledge of the noise. One that used a fixed upper bound noise. So the same upper bound that we use in the adaptive version and the adaptive version. So what you see is that the adaptive version starts behaving exactly like the one with the fixed bound. If you remember, when we were looking at the curves for the upper bound on the noise, there was this period in the beginning where it was fixed at the upper bound, and then when it had enough observations, it started converging toward the true noise. So that's what you have here. You have this period here where the model uses the upper bound on the noise, and eventually when it gets enough observations, then it starts following more and more what the oracle would do So behaving like an algorithm that knows the noise. So we were pretty happy with that and went on to applying our things to Thompson sampling. So fortunately, with the kernel regression provides you with a model, a posterior model, from which you can sample functions. So in the kernel TS algorithm, you sample one function and you act based upon that function. So as I said earlier also, you cannot just sample a function that is continuous. Like there's no way that you can sample an infinite amount of points from a multivariate normal distribution. Like you cannot call numpy.random.multivariate normal with an infinite mean and an infinite matrix. Or else I'd like to hear about that. So what you'll need to do is that you'll need to work on a finite discrete set for kernel TS, which is kind of a drawback when you compare with kernel UCB, but stochasticity might be nice, so the algorithm is still interesting. So what you do is just you take that discrete set and you just sample based on that set. So it gives you the function, the sample function evaluated at discrete points, and you pick the point in the discrete set which has the maximum value at the sample function. So when we were doing the theory, we find out that we were not able to come up with a result that did not suffer from the same problem as the analysis of linear TS. So, and by that, I mean that we need to inflate the covariance matrix when we sample the function. Apparently, we're not able to get the guarantees if we just sample from the posterior distributions. So what theory told us is that we need to add this guy here in our model, and this leads to also to an increase in the regret bound compared with kernel UCB. So that is the thing that we were less happy with. But still, we went on looking how it behaves in practice. So same example as before. We run the algorithm over a discretized set of 100 points, and what we find out are these curves where you have, similarly as before, the burning phase where you haven't started yet learning the noise, but as you get more information, more observations, then you start learning the good noise, and your kernel TS adaptative follows the behavior of the oracle. Okay, but you might be thinking, yes?
So in these experiments, you're doing the inflated version of computer?
Yes. Yeah.
Did you try in practice the regular?
Next slide.
Okay.
So we had this. So this is the Thompson sampling inflated. We compared it with kernel UCB. Kernel UCB this time on the discrete side. The previous kernel UCB was on the continuous space because, well, it can, so why not? And because it's interesting, we looked at what a non-inflated kernel TS would do. And, well, we did not want to inflate anymore. But theory tells us we should. So that's kind of where we are stuck right now. This is one of the challenges that we're facing. Like how should we? Is it a problem in the analysis, and we should not? And we should not be inflating, or is the inflation really important in some cases that right now we haven't been able to observe in practice? So this is still an open question in our heads. At the same time, we would expect kernel TS to be able to get bounds as tight as kernel UCB. So something tells me that the inflation might be a result of an analysis that is not tight enough. Okay, so I'll take it. Oh yeah, I have a couple minutes to give you a tour of how this was deployed in an application. So I'll present you a simplified version of the application, but just to give it, an applied side. I like to do that when we do theory. So it was applied, I'm working with people in the Servo Lab. So this is a brain research center. These people, they are brain neuroscientists. They want to take images of the brain, images that look like this. And to take these images, they use very fancy microscopes that cost a couple millions of dollars and that are super hard to tune. And when I talk about tuning the microscope, I don't mean that you buy it and then you need to tune it and then you're fine forever. No, I mean you buy the microscope and then you want to image living cells in rat brains. So first week you get your rat brains and then you take pictures and you see that your pictures are ugly. So you tune, you tune, you tune. Eventually you are able to take good images like this. And then next week you get rat cells again. But these rats, for some reason, they do not need the same parameters as the rats from last week. And not the same parameters like, oh, just switch a bit on the side. No, I mean, it can use parameters that are far away in the space of parameters to be imaged properly. So every time you get your new cells, every time you get your cells and you want to observe a specific condition and you go on playing with the fluorescent particles that are used to make the imaging, they interact together, they require imaging parameters that are different. So it's always a pain to find these, and you need to burn a lot of cells just trying to take a good picture. And in the end, when you are ready to take a good picture, then you find out that you only have, I don't know, 50 cells left instead of 500. So that is not very useful. So these people, well, what they would like to is they would like to avoid all these poor images that are taken during the tuning and get as much as possible these really good images like this, where you can observe interesting structures like the little rings you see here. So this is these are rings of a protein called actin, and they are researching this protein because it plays a role in Alzheimer's. So they really want to look at it and see how it behaves under different conditions. And so they want, I really like when Emily used the term, the expression learning during earning. So this is really what they want to do here. They want to tune their parameters while they are actually being proficient on taking images. So the baseline is usually they will discretize their space of search in a very small set of parameters because they need to take multiple images of each parameters to compensate for the biological noise. So let's say, for example, they want to optimize one laser power on their machine. They will discretize it in like 12 values. They know they will be taking 5 images per parameter. This would give them 60 images. What we do is that we tried kernel TS. Here we were playing with the non-inflated version, for obvious reason. So what we did is that we used the same discretized space as they were using with the grid search, and we run it on 60 images, so the same budget as they would do in their grid search. And the function to optimize was a function that tells you if there are any rings that are detected on the image. And so in this setting, we were not able to compute the regress because we don't have access to the true function underneath. So we were just looking empirically at trying to minimize the cumulative number of images that turn out to be bad, so that do not contain any rings. And what we found out is that, well, we are able to accumulate like 4 images at a rate that is much lower than obviously what you would do with a grid search. Well, this is clearly not the best way of quantifying the performance because this curve is subject to the noise. Like you accumulate, it ends up accumulating 4 images even if it is sampling at the best possible parameter just because there is some noise in the values. So you can never avoid this linear growth, but it's still a lot better than what they were using. So right now in their lab, they're using kernel TS everywhere. They are optimizing everything. It's fantastic. Yeah, sure.
So
Yeah.
So do they keep using kernel TS afterwards, or it's just during the 60 first images that they use that, and then they keep on the same parameters?
Here I reused an experiment that was used for my thesis, so it was just 60 images, but
Okay.
usually
So
they do, yeah, it's more in the hundreds, but they need to restart, like every time they get new cells, they start again, but they will be taking a couple hundreds. And among those couple hundreds, usually they have like 30 images that are not so good, but they get really good. And they get better also than what they would be able to do with the grid search. Because with kernel, here, in order to compare, we discretize the same way as they discretize with the grid search. But now that they're not doing the grid search anymore, with only kernel TS, they discretize in a much finer way, such that they are able to find parameters that are a bit more adapted to what they would. And they cannot use kernel UCB here for other reasons that I won't discuss. Like I said, the application is much more complex. They have other things that interact, but being stochastic and not relying on optimism was one of the requirements for that application. That is why kernel TS was so important. So just to wrap up, we were really happy to be able to provide guarantees even in the setting where the noise was not known, and we were really happy to see that the results would translate very quickly to kernel bandits. Like it applied, like the proof of kernel UCB fits in one page. It's super easy, and these results that hold that hold uniformly over T are pretty nice. Also, I think they have more application to just standard regret. And but we still have some open questions, especially regarding the apparently suboptimal analysis of Thompson sampling, which I'd be very open to discuss. Thanks.
So your scheme for tuning the regularization parameters still requires to know this parameter C, that is an upper bound on the norm of the function, right? Or
Yeah, we still need to know an upper bound on the norm of the function.
would you be able to adapt to that as well?
Well, if we could remove we could remove the dependence on the norm of the function by making a different assumption on the covariance that generates theta. Like we could cast ourselves in the Gaussian process setting and depends only on the noise in the regularization. But this would be like assuming that we know the norm of the function, because we would be pushing it back in the kernel. Like if you relate to in the Gaussian process setting, their regularization is equal to the variance, the noise variance. They don't have this dependence on the norm of the function because the sigma is inside the kernel. In this case, we explicited the sigma, but I think you cannot avoid it in any way. Just the fact that we know that the kernel, that the function belongs to the kernel space is in itself a pretty strong assumption that is related to that.